Your essential question today is the same as it was yesterday, which are, how are the subatomic particles in an atom related to each other? Your code's 410. Your pages are 53 and 54 today, 54 where your notes are going, and then your topic is atomic structure. First little bit is this. And if you already know it, because we've been doing this for a while now since before the break, if you already remember this, you definitely don't need it down again. But it's having you get down in your notes officially now that the atomic number is equal to the number of protons, which we've done over and over, but you don't have it in your notes yet. So now it's official that the atomic number is the number of protons. And I think you guys probably remember that because we've done it about 3 days now. We've done that system, right? In your periodic table, in the boxes in there, which number is the atomic number? The one on the top of the box or the one on the bottom of the box? The top. It's also the number in the box that is the whole number. If it's got a decimal number, that's not the number you want. That's the mass number. Remember, when you do your memorization for this, the first 18 elements, it is name, it is number, Ashton, and it is the abbreviation, Ashton. Okay. Are you focused? Or are you making weird faces at Jair? Classic. Okay. So, let us proceed then. The next piece of information that you guys have written down a couple times, but just not put in your notes, is this one. And that is how to get that mass number. And that is that mass is equal to protons plus neutrons, right? So these are things you'd probably want to highlight in there because these are big deal things. Things I guarantee you are on the test, like having to do this stuff. So these things are 100% certain on the test. As a follow-up question to this one, or this point, if you had the mass, right, and you have the protons, how can you get neutrons? Right. That is mass minus protons equals neutrons, because I guarantee you that pops up again too. It's been on our homework a couple times, and I'm 100% confident that that shows up on the test. There's no doubt in my mind from the man who made the test, the immature man who made the test, I guarantee you that that's on there. Last bit on this page that you got to get down is this. That when we measure mass, we measure like how much you weigh, and in the U.S. we measure that in pounds, or if you go someplace else, you measure it in kilograms. When you measure atoms, that number that's down at the bottom is called atomic mass units. That's the label for it, AMUs. They make it as simple as they possibly can. Each proton is 1 AMU. It weighs 1. Each neutron weighs 1, so they make it as easy as they possibly can, right? If you got 7 protons and 7 neutrons, that's a mass of 14 AMU. That's how that works out. So it's just as simple as can be in terms of how mass is labeled up there. True. So periodic table information you got to have. Again, this is stuff that you know, but we haven't put in notes yet. So if this seems redundant, if it seems like, why am I writing this down? That's good, because that means you know it and I've been doing my job. But this is like the official let's get it down inside of your notebook stuff. The number on the top in each box on the periodic table is the number of protons, and it's called the atomic number, right? And I'm confident that 85% of you know that, because we've gone over it 3 days in a row, or 3 days, 4 days worth of stuff. We haven't put it in your notes yet, so this is the official let's get it in our notes thing. That number on top is called the atomic number, right? So if we're looking at it, it is, I think I've got an arrow pointing to it right here. This number on top, like 80 is mercury if you look up there, that is the atomic number up top. The number down on the bottom, officially now, the number down on the bottom is called the mass number. And that is the sum of the protons and neutrons, except on the periodic table you'll notice they're all decimals, and that's because they do this thing called a weighted average. And I'll explain that as best. So, next key point is what's the difference between the types of atoms. There's only one meaningful difference between hydrogen and helium, helium and lithium, lithium and beryllium. And I think you already know it. What is the thing that makes hydrogen different than helium, that makes helium different than lithium? There's one thing, It is the number of protons. Very good. So, and that's a key point. I guarantee you, you might want to highlight this or put a star beside it, whatever. I guarantee you this is on the test. That the difference between elements up there in terms of what makes them different, what makes hydrogen different than helium, only has to do with the number of protons that are in it. There's only one thing in the whole universe that we're aware of that has one proton, and that's hydrogen. There's only one thing in the whole universe that we're aware of that has two protons, and that's helium. So that's what makes different elements different, is their number of protons. The number of neutrons and electrons that they have do not influence, like, the name of the element. They affect how much it weighs, they affect how much, or its different chemical properties and physical properties, but they do not affect what it is. It's still hydrogen, it's still helium, it's still potassium. They just affect positive, negative, right? That's electrons. You can make an element positive, you can make an element negative. They affect whether it's an isotope or not, and that's neutrons, but they don't affect what it's called. You know it, because we've gone over it multiple times, but I want it officially in your notes too, because I know we've talked about it over and over, but since this is only our second time doing notes, I want to make sure it winds up in there. And that is that protons and neutrons are the things that are inside the nucleus, the center of it. And they are, the second piece of that is, they are the pieces that account for or cause or add up to the mass of the atom. They are the things, protons and neutrons, are in the nucleus and are the things that make it have mass. The electrons are really small. Like I said, it takes about 7,000 of them to equal a proton. And they occupy the largest space. We talked about that yesterday. It'd be like taking a volleyball into a football stadium, putting the volleyball on the 50-yard line, and that would be the nucleus. And the whole rest of the stadium would be where the electrons live. But they're very, very small. The electrons themselves are super tiny compared to the proton. 1/7,000th of a proton. But they move all over and they take up a lot of space that way, if that makes sense. So it's like your really like hyperactive cousin or something like that. They're tiny, they're a little bitty kid, but they're so hyperactive they're all over the place, and you got to give them a little room because they're always spinning their arms around trying to hit things. So you just give them some space. That's kind of electrons. They're really tiny, but they move really fast and take up a lot of room because they move really fast. But the question, right, how do the subatomic particles balance each other out? And inside an atom, on the periodic table, we've talked about it, the protons and the electrons are equal, or they're supposed to be equal, right? And that's because they cancel each other out. So the question is, if you had 20 protons present in an atom, what element are we talking about if you got 20 protons, first of all, using your periodic table? Very good. Ca, calcium on the very left-hand side. Then there's 20 electrons there to balance it out because the positives are canceled out by the negatives. 20 protons, 20 electrons. The neutrons, you can have a different number of because they don't add into the charge. They don't add to the charge. They don't subtract from the charge because they don't have a charge. What's that? They change some of the chemical and physical properties when you change those numbers. Like I talked about with hydrogen, if you add some in, you can make deuterium, which is used to make heavy water and cool nuclear reactions, or you can make tritium, which is radioactive and glow-in-the-dark stuff that's really expensive. Sorry, Cecilia.